This lecture refers to implicit differentiation. Let me write that down. That was an L if I can fill it in. Alright, if you try to take this equation that I have here, an ellipse with major axis radius equal to 5 and minor axis radius equal to 3, it's not a function. In fact, if I draw a vertical, well, you can see there's vertical lines going through there. Here, let's just follow one of them, or about that. This thing fails the vertical line test. From now on, I will refer to that as VLT, if I ever need to use it again. So the equation fails the vertical line test. So far, all of our derivatives have looked like this. F prime of x equals something in x. That is, you've been able to get y on one side and x's on the other side. But sometimes you can't do that. Look at this. Now, I can take this thing. Let me grab it here. I don't want to actually grab it, but if I want to get my calculator or your calculator to graph it, you have to try to get y by itself. So, to make a calculator graph it, solve for y. So let's go ahead. If I have x squared over 9 plus y squared over 25 equals 1, the first thing I would do, I guess I would probably multiply both sides by 225. Why would I do that? Because it'll clear the denominator. So if I go 225 times this whole equation, here's what I end up with. I have x squared, I think it's 25x squared. 25 times 9 is 225. Plus 9y squared equals 225. Next thing I would do is subtract 25x squared. So I have 9y squared equals 225 minus 25x squared. Divide through by 9. Y squared equals 225 minus 25x squared over 9. And then take the square root. Y equals plus and minus the square root 225 minus 25x squared over 9. I think what I'll do is I'll grab this guy later. So what you would have to do in your calculator then is you would have to do something like, and then y2, you can press negative y1. This part here gives the top half. So that will give the top part of the ellipse, and the second one gives the bottom. So you'll get it to go that part there. Alright, let me scroll back up to it. The really cool thing about this is even though we have defined derivatives to be functions of x, we can still find derivatives without actually having y explicitly solved for. If you look back here, this is called an explicit solution right here. That's where I'm able to get y on one side and all the x's on the other side. However, if you go back up to this thing, it's certainly true that if I'm at a certain spot on this thing, I don't know where I want to pick, but let's just pick something, I don't care really, say over here. Isn't it true that if I'm interested in only that part, or that particular point, if I'm interested in finding the derivative, or the slope of the tangent line at that point, I mean, after all, the thing does still have tangent lines. If I really want that there, then this portion, if you will, the top half does fulfill this, the top half is a function. Similarly, if I had a point, say, way down over here, I would ignore the top half and pretend like I'm working in the bottom half for this case. Well, that's what explicit differentiation is. It's where you have to have y as a function of x. It's got to pass the vertical line test. Implicit differentiation permits you to do the differentiation without necessarily having to have y as a function of x, nor do you have to have x as a function of y. It works from a relation standpoint. So, we saw how to graph it. I'll work with you guys later. Let me go ahead and call up that graph again. I'm going to go to my... Alright, let me go back to the equation. We have x squared over 9 plus y squared over 25 equals 1. Alright, what I want to do is find the... I need to stop using the word the because there's several possible answers. Find equations for all tangent lines through x equals 1. So if I look at x equals 1, I can see that, let me use the mouse to highlight this. When x is 1, if I go straight up to the graph, I have a spot here that will have a tangent line. And the tangent line will almost certainly have a negative slope. Okay. Now if I go straight down, there's another one for the same x value. And that one will most certainly have a positive slope. So first, let me find out these points. So the points with x equal 1, that's where I'll replace x with 1. So I have 1 squared over 9 plus y squared over 25 equals 1. So I have 1/9 plus y squared over 25 equals 1. I'm going to subtract 1/9 from both sides, so y squared over 25, I need to take it easy on those y's, equals 8/9, and then I'll multiply both sides by 25. So y squared equals 8/9 times 25. I'm not actually going to multiply it up because I'm going to take the square root next. So y equals plus and minus the square root of 8/9 times 25. So this is equal to, well, the square root of 9 is 3. That's easy enough. The square root of 25 is 5. So I'll have a 5, and the square root of 8 is 2 radical 2. 5 times 2 radical 2 is 10 radical 2. So let's put those on the graph. So my point, I'll have 1, that was 10 radical 2 over 3. And then the other one is 1 comma negative 10 radical 2 over 3. Alright, now the way you take the derivative is very interesting. You don't actually go, I did do some solving for y here because I had to get a point. But I'm not explicitly going to solve the equation for y. What I'm going to do is this. Remember that the derivative, d over dx of x equals 1, and d over dx of y equals, well, we call it d over dx of y equals, well, we just call it dy over dx. You might find it useful, at least more convenient, if you just simply call it y prime. Just like we do f prime of x, things like that. Alright, here's how we go. Start with our equation, x squared over 9 plus y squared over 25 equals 1. And remember, we are implicitly assuming that y is a function of x. That's why I'm doing this. I'll simply take the top half or bottom half as needed depending on the point. I'm going to take the derivative with respect to x of both sides of this equation. Okay, the derivative of a constant is 0. The derivative of x squared is 2x. Here's where it gets complicated. You need to think of y squared as being a function inside of a function. In fact, y is a function of x. Okay, so if you want, think of y squared, if it's easier to think of it this way, as y in parentheses to the second power. That way, when you take the derivative, you'll think to take the 2 out front, so you'll do 2y, but then you'll take the derivative of what was inside. And that's why we end up with 2y times y prime. So 2y times y prime over 25. Now what I'm going to do here is solve for y prime, the derivative. So I'll subtract 2x over 9 from both sides. Okay, I'm going to do something real quick. I'm going to divide 2 from everything. Right now instead I'm going to subtract x over 9 from both sides. If these actions seem similar to what you've seen before, it's because you have. When I was solving with numbers, I was doing the same steps. I have y prime over 25. Now if I want to get y prime by itself, I'm going to multiply by 25, but then I'm going to divide by y. So I'll have negative 25x divided by 9y. Now, what you gain in convenience is sacrificed here because I do not have my derivative in terms of just x. So it's not a function either. However, I do have my points. If I want to get those tangent lines that I talked about earlier, what are the equations of the tangent lines through the the point one comma plus and minus 10 radical 2 over 3. Well, all I gotta do is plug those numbers in. Let's start with this one. 1 comma 10 radical 2 over 3. Well, that was the one on the upper half of the ellipse. So the slope of the tangent line, I'm going to put y prime. Here's a notation that you can use. Some people put 1 comma 10 radical 2 over 3, sort of to remind themselves that y prime actually has two arguments, both x and y. But anyways, the slope is whatever number I get out of this. I have negative 25 times 1 all over, and then I have 9 times 10 radical 2 over 3. Well, that's nice. It simplifies a little bit here. See, I can take this 3 goes into 9 3 times, so I have negative 25 over 30 radical 2. Oh, this actually does a pretty good job of simplifying. I'm going to have negative 5 over 6 radical 2. Don't worry about putting the radical in the numerator. It does you absolutely no good. So what is the equation of that line? Well, the equation of the line is y minus y0 equals m times x minus x0. Let me put my numbers in. Y minus my y0 is negative 5 over 6 radical 2. No, that's the m, sorry. 10 radical 2 over 3 minus 5 over 6 radical 2 times x minus 1. In order to get your calculator to graph it, you don't have to specifically solve completely for y and put it in the format of slope-intercept form. This will get you far enough. Leave the negative 5 over 6 radical 2 x minus 1. Leave it alone. And then just put plus 10 radical 2 over 3. The calculator will take the input, and you won't have to. It'll save you one step. Not only do we have the point listed here, we have 1 comma 10 radical 2 over 3 goes through that point, and the equation of the line itself is y equals negative 5 over 6 radical 2 times x minus 1 plus 10 radical 2 over 3. So that's the equation of the tangent line. I'll leave the other half to you, the bottom half, this point down here, negative 1. You know you're going to have to get a slope, a positive slope. Up here, let's go back to this for a second. This slope is obviously negative. You'll probably, if I had to guess, you're probably going to get the positive version of that. Give it a try and see if you can get that. Graph the bottom half and see how it stacks up. Now there was another equation I wanted to do. Alright, another equation I want to graph looks like this. X squared minus xy plus y cubed equals 1. This would be very difficult to solve for y by itself and under any circumstances. Let me pull this one in. This is how it graphs out. You can see that it does not pass the vertical line test. But let me get the derivative. I want to find some interesting points here about it. I want to try to find on this graph places where the tangent line is horizontal, like up here. Let me see if I can, up here somewhere the tangent line is horizontal. Over here the tangent line is vertical, and over here the tangent line is vertical. So I might be interested in figuring out all those things. It's clear that it goes through the points negative 1, 0 and 1 comma 0. First thing I'm going to do is take the derivative of everything with respect to x. D over dx, x squared minus xy plus y cubed equals d over dx of 1. Alright, the derivative of x squared is easy. That's 2x minus. Now you got to keep in mind, this here is a product of x and y. So remember how that works. The derivative of the first times the second plus the first times the derivative of the second. So I'll put this down here. I'll just remind you of it. D over dx of x times y alone. Then we have plus x times d over dx of y. You have to use the product rule for that. Plus, now, y cubed, the outer function is to the third power. So the first thing you do is 3y to the 2. And then what's the derivative of the thing inside? That was y. We're calling it y prime. The derivative of 1 is 0. Let me go ahead and finish up the details in the parentheses. The derivative of x is 1, so I have y plus x y prime, because the derivative of y is y prime, plus 3y squared y prime equals 0. Simplify a little bit more. I have 2x minus y minus xy prime plus 3y squared y prime. Let me make that y prime look reasonable. Now, in order to solve for y prime, the first thing I'm going to do is get rid of the 2x and the minus y. So I'll have negative x y prime plus 3y squared times y prime equals negative 2x plus y. Next, I'm going to factor out y prime. I have y prime times negative x plus 3y squared equals negative 2x plus y. Then I'll divide by negative x plus 3y squared, and I get my y prime equals negative 2x plus y all over negative x plus 3y squared. If you don't like that, this is the same thing as y minus 2x divided by 3y squared minus x. Some people like that a little bit better. Alright, so before I answer the questions I did before, can you, what is the slope of the tangent line when y equals, let me go back up here, let me see how y goes. I'm going to say when y equals 1, right there. So I'll know x will be equal to 0, but when y equals 1, are there more things than that for y? There'll be another one over here. See this? So I'll have a positive one most likely, and then I'll have a negative one. A slope of a negative one. So I'll have two x values with this one y value. So let's plug them in. X squared minus x times 1 plus 1 cubed equals 1. I have x squared minus x, oh this is easy, equals 0. X times x minus 1 equals 0, so this occurs at x equals 0 and 1. So I have 2 points. I have when x is 0, y is 1, and when x is 1, y is also 1. Keep that in mind. Let's go ahead and plug those into my formula that I have up here. I'll use this version of it. So I'll write this y prime for the point 0, 1 equals, keeping my eye on this at the same time, 1 minus 2 times 0 all over 3 times 1 squared minus 0 equals 1/3. So I have a slope of 1/3, and the equation of this line, so the I'll call it L sub 0, 1, so you know that's the line through 0, 1. We have y minus y0 equals 1/3 third times x minus, well, I should have probably just put that a 1 right there. Or y equals 1/3 x plus 1. Let's graph that and see if it actually hits in the right spot. So I'm going to go back to my GeoGebra, and we will put y equals 1/3 times x minus 1. No. Boo-booed. Plus 1. Look at that. Right there it is. Perfect. Perfect, perfect, perfect. Let me go ahead and grab a picture of that thing. I don't know how much I would blow that one up, but I want to. Here we go. Stop growing. Alright. So we have the point that this is occurring at. I'll try to make a huge thing here. Is 0, 1, and the equation of the line is y equals 1/3 x plus 1. I can't, the other equation will probably be similar, so see if you can solve that one, do the same process that I've done, and see what you get for the other equation, the other tangent line equation. I actually solved more than I had to. The actual answer to this question up here was 1/3. I went farther and found the equation of the tangent line. So, you might want to do the same thing if you can. I've mentioned this before. You might want to download this thing called GeoGebra Classic. You can download that. I have another program here called Graph. Graph, if you go under Function, you can insert the relation in there, and it will draw what I have drawn for you. So, and then you can draw the tangent line, or what you think is a tangent line, and see how much it works out. All right, so that's pretty nice. There's a couple other questions that I wanted to ask. Let me grab this picture again. I'm interested in around here, because this is where all the questions I was asking came from.
Draw exactly where I went down. That's not bad. You can see somewhere around there I have a horizontal tangent line. And then if you look somewhere over here, I have a vertical tangent line. And then I have what looks like another, let me get over. Another one. So, why are those so important? Well, they typically do represent asymptotes and things like that. However, they also represent extreme situations, things where mechanical processes start to break apart, resonances occur, things that are uncontrollable occur because of these extreme, well, at least the vertical ones are. The horizontal generally means things are stopping. So, can we determine where there are horizontal and vertical tangents? I probably should not use plus for that. And vertical tangent lines. Can I do that? Well, let me go back to the derivative. Where was it originally? We solved right here, this thing up here. Y minus 2x, 3y squared minus x. 3y squared minus x. Let's take a look here. How can we determine where they're occurring? Now, I'm looking at my graph, and I'm not sure where this point occurs right here, but I do know if a horizontal tangent means that y prime equals 0 for a horizontal tangent, because horizontal lines have 0 slope. So if I look there, if I had to guess, it looks like I have x. I don't know what it would be, but it might be 1/2 and y might be 1. Is that true? To equal 0, we would have to have y minus 2x all over 3y squared minus x equals 0. Now, assuming the denominator is not equal to 0, I can multiply through by it to get y minus 2x equals 0, or y equals 2x. So whatever x is, y is twice that. Now, can I actually get something out of this? I mean, so far this is the best I can do because I've solved for y prime. But can I quite figure out where that is by any other means? I don't think that I can. What I can do, though, x squared minus xy plus y cubed equals 1. Now I'm going to take y equals 2 of x and plug it in. So we'll have x squared minus x times 2x plus 2x cubed equals 1. Well, this is going to be bad. I'll have x squared minus 2x squared plus 8x cubed equals 1. So 8x cubed minus x squared minus 1 equals 0. Now let's throw that into the calculator to find out approximately what the 0 is for x. So I'll go to my Wabbit. Y equals, let me change that to, just delete it out of there. And zoom 6. Let's see what happens. Okay, now you can use your calculator's calc button. Go to second, trace, and it will give you the calculate area. Hit 2 for 0. If you remember, when you want to estimate these things, go to the left of where the 0 is, because it wants a left bound. Then move the cursor to the right of the 0. Oh, I didn't mean to jump off screen, although you could, it wouldn't matter. Hit enter there, and then go somewhere in between, a guess it calls it. The closer you get, the faster we'll do it. Alright, let me grab that thing. So, let me see, my x is approximately 0.545. Now, one of the things that I had to have is y equals 2x. So y is going to be approximately, see it? Alright, and let's see how they actually fit into the original equation, which was x squared minus xy plus y cubed equals 1. I just want to see how good of an estimation that I have. I'll have 0.545 squared minus 0.545 times y is 1.09 plus 1.09 cubed. And that's supposed to equal 1. We'll get an approximate value here. So let me use the calculator for that. Let me get out of there. 0.545 squared minus 0.545 times 1.09 plus 1.09 to the third power Enter. Pretty close. The calculator gives me 0.998. 0.998. Obviously, you could simply grab more decimal places right here if you wanted to, and multiply it by 2 to get the y value, and you can get as much accuracy as you probably could want. All right, talked enough about that in detail. Hopefully, you get the idea on how this stuff works. There is one last application. So far, we have the power rule goes like this. Y equals x to the n, y dy over dx, or y prime, equals nx to the n minus 1. And that was for any n in the integers. Except 0. Let's put that, let me take that out of there. Because if you have something like y equals x to the 0, and you wanted to come down with the 0 out front, you have to the negative 1. No, yeah, so take that out of there. That's the only thing it doesn't work for. Alright, but it kind of does work for it if instead of y equals x to the 0, you think of x to the 0 as 1, then the derivative is just 0. Anyways, we want to extend this to rational numbers. So suppose y equals x to the n divided by m, where n and m are both integers. Okay, next thing I'm going to do is take both sides to the mth power. So you end up with this equation. Now I'm going to take the derivative with respect to x of both sides. Remember on the left side to use the chain rule. The outer function is to the mth power. So you have m y to the m minus 1 because m is an integer. But don't forget to multiply by the y prime that is the inner function. That equals nx to the n minus 1. Now what I'm going to do is solve for y prime. So I'm going to divide by all this other stuff. I'm going to divide by y, or m, y to the m minus 1. Divide the other side by m, y to the m minus 1. And I have y prime equals nx to the n minus 1 divided by m y to the m minus 1. Now let me go back. What was y to the m equals x to the n? So let me come over here. This is nx to the n minus 1. I'm going to leave that alone for a minute. Y to the m times y to the negative 1. Y to the m, I just put it up there as x to the n, so I'm going to change this to n x to the n minus 1 divided by m x to the n y to the negative 1. Now I'm ready to simplify that numerator a little bit. I'll have n x to the n times x to the negative 1 divided by m x to the n y to the negative 1. So let me cancel these out. Now here's a cute little thing that happens next. N y divided by m x. Let me fix that m. Because the y to the negative 1 becomes y to the 1 when you take it up there, and vice versa. Now, where was y again? Y was equal to x to the n over m. That equals n over m. I'm going to separate this out. Y was x to the n over m. Down here is x to the 1. This equals n over m, x to the n over m minus 1. What that means is the power rule works for rational exponents. Hit it's not that it all of a sudden started working. No, it now works for them because we recognize through this implicit differentiation that we're able to get to here. So the power rule now works for rational exponents. And that is all I'm going to do today. That was pretty hefty.